Hi guys, I'm Jack McDonald. I'm a 15-year-old innovator with the Knowledge Society, and I'm pumped about AI and machine learning and their future applications in the world. The topic of this video is reinforcement learning. In the video, I'd like to give you a nice, brief understanding of reinforcement learning and the calculus powering this algorithm. Before I begin, however, I believe it's necessary to get a good understanding of AI, the large umbrella under which reinforcement learning and machine learning fall. So, first off, what is AI? Why should I care and why should you? Well, put simply, AI is the artificial computation of human intelligence. AI is able to replace humans in many jobs as a result of this, and the applications currently are vast. Most powerful, arguably in my mind, is the power of AI to understand patterns in large pools of data and create meaning for companies that they can in turn create monetary value out of. The branches of machine learning, arguably the most powerful sub-branch of AI, include unsupervised learning, learning without labels of data, supervised, labels with data, and reinforcement learning, the topic of today's video. So, what is reinforcement learning? Reinforcement learning, as I said before, is the sub-branch of machine learning in which the computer learns by continuously doing a task and improving. It does this by utilizing the power of reward. Just like you learned your ABCs or you learned how to teach a dog how to sit by giving them treats or giving them compliments. The computer learns by understanding, at a mathematical standpoint, what actions are good and what actions are bad. What destinations are good and what destinations are bad. What steps to take in order to reach the optimal goal. And this is what really is interesting about reinforcement learning. But to get a further understanding of this, I believe it's necessary to dive into the calculus powering this algorithm.
The purpose of widespread reinforcement learning problems is to solve a specific set of problems referred to as MDPs, or Markov decision problems. These problems contain four aspects. The first being S states. The second being a set of A actions. The third being a transition probability function. And the fourth being considered the reward function. The explanation of the first two aspects of MDPs are quite simple. Where calculus truly gets involved and where value is truly added are the last two, in the transition probability function and the reward function. As seen in the outline of the transition probability function on the screen, the purpose of this function is to assign a probability distribution that represents the probability of entering a state S using action A. The result of this calculation will show the degree at which that certain algorithm, that certain set, should be rewarded. The last, reward function, describes the reward associated with entering each state using an action AT. This process is repeated until the code is considered optimal. The final and somewhat unrelated step in this process is considered to be the future discount factor. This simply represents how much we care about future rewards given the reward function and the transition probability function.
Before I officially sign off, I'd like to tell you one quick story about the application of reinforcement learning at a company over the Atlantic Ocean called Wave. Now, Wave is an autonomous vehicle company, and unlike other companies, they're not terribly well funded. They're a startup, and the barrier to entry in this space is very high. Wave needed another way. They couldn't hire engineers on a few $100,000s of salary. They needed a way to create an efficient system of driving with only one engineer and an onboard computing system. How could this be done? It couldn't for a long time, at least theoretically. But then they came upon the concept of learning by reward, reinforcement learning at Broad. Thinking about this, they understood that this could be integrated into AVs, autonomous vehicles. After tests, it proved successful. In fact, in one experiment, through reward and manual control, the company was able to teach a car to lane follow in just 20 minutes. Now, to put this in perspective, it took the Google team roughly 2 years to accomplish somewhat of the same feat. It took researchers at Carnegie Mellon 9 months to even have a good understanding of how cars could conceptualize the roads. This is just a glimpse into the power of reinforcement learning, and I hope you all now, after having a good understanding of the calculus, can formulate your own ideas as to the future applications of this technology.